Hi everyone, I want to go over lesson 2.6 with you right now. This is on resonance and formal charge. So by the end of this lesson, I'm actually going to split it in half. You're going to be able to represent a molecule with a Lewis diagram accounting for resonance between equivalent structures, or using formal charge to select between non-equivalent structures. I will explain what all that means. Basically, when you're drawing Lewis structures, sometimes there's more than one equivalent structure that could be made. And so this concept of resonance must be included to refine the Lewis structure and give a more accurate prediction of the structure of the molecules and therefore its properties. Also, octet rule and formal charge can be used to determine which Lewis structure is best for structure and properties as well. The main thing is the Lewis structures that we've been looking at, there's some limitations, especially if your electron number is a little bit weird. So the idea of resonance, if you can make one or more valid structure, or actually more than one valid structure that obeys the octet for a molecule, they're called resonance structures. What's really important here is you're not moving the atoms around, you're just moving the bonds around. So in cases where like you've determined, oh, I need a double bond to that center atom, but there's multiple choices that I could choose from, that's where resonance comes in. What you would do is you would draw the different possible structures and then draw double-sided arrows between them to show that they are equivalent. Also, typo, the actual structure is an average of the resonance structure. So if I took all of my resonance structures for a molecule and like superimposed them on each other, it would be kind of a blur. This refines this localized electron model. The Lewis structures, when we draw them, we tend to think of, oh, the electrons are between these two atoms, period, end of story. Resonance says, no, they're actually delocalized, and the electrons that are involved in a molecule as a whole can move around the entire structure. So the example, you have it on your slide for the nitrate ion. I'm going to show you how it comes about. So the nitrate ion can be written three different ways. So we always start out with our basic counting, right? So nitrogen has 5 valence electrons. Each oxygen has 6 valence electrons. And then we need one more electron because this ion has a -1 charge. So we have 24 electrons that have to go into our picture. The nitrogen is our center, and then we put our oxygens around the perimeter, attach them each with a bond, so that's 6, so there's 18 left. So when we draw in those 18 electrons, we're now out of electrons. However, the nitrogen is not obeying the octet yet, and it needs to. So I have options here. I can take a pair of electrons from this oxygen on the left and swing it in to make a double bond, or I had the option to do the same thing with the oxygen on top or the oxygen on the right-hand side. None of those are, like, there's no one good choice here. They're all valid choices. Oh, and since this is an ion, I want to put them in brackets. So what you see in the, when you draw resonance structures is you're going to draw all the possibilities. So notice I did not move the atoms around. Okay, all I did was I floated that double bond into the different possible locations. When you put the double-sided arrow in between them, it shows that any of those are possible. Now, when these bonds are experimentally measured, any of these bonds between a nitrogen and an oxygen are not a strict single bond or a strict double bond. What they actually show is that they are somewhere in between a single and a double bond, approximately the length of 1.3 bonds, because we're dividing that double bond into 3 possible locations. So again, notice the arrangements did not change. We just floated that bond around. So the correct Lewis structure is not given by any one particular one of those structures, but the superposition or the average of all 3. This link is a short YouTube video. It's really good. It's live on your PDF. You could click it, or I'll probably post that video in the section if I haven't already. Another example would be ozone. Okay, so let's look. Oxygen each has 6 valence electrons, and there's 3 of them. So I'm going to do 18 electrons here. So I start by connecting them with single bonds, and then I start to draw in my electrons. So that's 16. I have 2 electrons left. So I put them on my center oxygen, but the problem here is that center oxygen does not have a completed octet. So I have the option of pulling a pair of electrons from the oxygen on the left to make a double bond, or I had the option of pulling electrons from the oxygen on the right to make the double bond. So those are the two resonance structures for ozone, right? There's choices here. I did not put these in brackets because they're not polyatomic ions. So I did not change well, obviously it's oxygen, so whatever, but I'm not changing, like I'm not making these into a triangle or anything weird. I'm just moving the double bond into the different possible positions. So it just shows you it's a hybrid of the two. Now this shows you the actual data. So the true bond length of an oxygen to oxygen single bond is 148 picometers. The true bond length of a double oxygen bond is 121 picometers. And then the actual bonds in an ozone molecule are approximately 128 picometers, which is not exactly halfway between, but it is between the length of a single and a double bond. So these bonds would all have a length of 128. Here's another example for N2O4. So nitrogens each have 5, oxygens each have 6. So I need 34 electrons in my diagram. So I'll put the nitrogens in the center, and I'm going to branch these oxygens off. Don't worry about the shapes. Okay, so right now there are 10 electrons. I need 24 left. And I'm going to eat up all 24 of those electrons by completing the octets for those oxygens. But the problem is that each of my nitrogens still only have 6 valence electrons. So I have choices now. I can pull, I could pull those into a double bond, and I could pull those into a double bond. So I could do this. Okay, but I also could have chosen where am I? This. Or I could have chosen this. Normally you're not going to have 4 resonance structures to do, but there's 4 here. Or I could have done okay, this. Okay, so there's 4 different possible resonance forms and just moving those double bonds around. Okay, last example here for resonance is CCl2O. So all of these are possible structures. Now for these, there are different ways to arrange the atoms. So these are all the same arrangement, but the electrons are changing. These are all the same arrangement, so the electrons are changing. These are all the same arrangements, but the electrons are changing. One of these does not work, and it's this first one on the top left because the carbon doesn't have an octet and it needs it. So that top left one is out automatically, but all of these other ones are possible okay structures. So we can also have a method to determine which is the best of all of these particular structures by using something called formal charge, which I'm going to put into a separate video right after this one. It leads into it. So thanks for coming.